Okay, today we're learning techniques for evaluating limits when direct substitution doesn't work. So last lesson we substituted a value in, like 0, for the limit as x approaches 0, and we were able to find the value of the limit just by substitution. That works very well with polynomial functions because polynomial functions are continuous everywhere. And so anywhere I want to plug in an x value, I can find the corresponding y value. It works pretty well in rational functions too, as long as you're not trying to evaluate the limit of a rational function at its asymptote or at a whole. You'll still be able to use direct substitution to plug in an x value and find a y value, for example right there. But today we'll find some functions where we need to do some work in order to find the limits. Two special trig limits you need to know are the limit as x approaches 0 of sine x over x. So if you just substitute 0 right in, we have sine of 0 over 0. The sine of 0 is 0, so we get 0 over 0. 0 over 0 is called the indeterminate form, and this always is going to tell you that even though there's a problem with this limit, we can fix this problem. So anytime you get 0 over 0, this is a fixable problem, and we can still find the limit. But for these two special trig limits, we're going to ask you to memorize them, because without a calculator, they're very difficult to find out. So if we do have a calculator, we can take a look at sine x over x and see, as x approaches 0, what y value are we approaching? And while we're at it, we'll also look at 1 minus cosine x over x, because 1 minus cosine of 0 is 1, so this would also give me 1 minus 1, which is 0 over 0. So both of these trig limits are going to be the indeterminate form, and we need to find our limit in another way. So I'm going to look at the graphs. For sine x over x, this is my graph below. And you can see that as the x values approach 0, from the left and from the right, we're approaching a y value right there of 1. And you can see that as well from the table of values. For 1 minus cosine x over x, here's our graph. As x approaches 0 from the left and from the right, you can see our y values are approaching 0, and you can see that from this table of values as well. Notice the error tells us that if you actually just plug 0 in, that value will not be defined, but that's okay for limits. For limits, we're just trying to figure out what y value are you getting really, really close to. So the limit as x approaches 0 for sine x over x is going to be 1, and the limit as x approaches 0 for 1 minus cosine x over x is going to be 0. So let's go back to our notes and fill those in. The limit as x approaches 0, sine x over x is 1, and this one is 0. So please make sure you memorize those two, and later on in our notes we're going to be using those values. So now we have a set of problems. We're going to try substitution to see if we can just substitute a value in and get our answer. If substitution doesn't work, then we'll see what can we do analytically to fix our problem. So the first one is a pretty long rational function, so I plug this in our calculator, and my numerator is 213, my denominator is 51. So if you were to divide that and press math fraction, that would help you simplify your fraction, 213 over 51. Or you could recognize that 3 is a common factor of the numerator and denominator, and when you divide it, you get 71 over 17. So in this issue, direct substitution worked just fine, plugging 2 in. In problem 2, we can plug 3 in. We get 3 squared minus 3 minus 6, 3 minus 3, which gives us 0 over 0, which means we have a problem, but we can fix it. In this case, we're going to solve our problem by factoring. So if you factor your numerator, we get x minus 3 times x plus 2, and the denominator is x minus 3. So because this factor cancels out, that tells us there's a hole in the graph. But the hole is fine for the limit. We can still have a limit as x approaches 3. And now I'm going to plug 3 into the remaining part of my function, which is just x plus 2. I have 3 plus 2, so the limit is 5. In problem 3, direct substitution gives us 1 minus 1 over 1 minus 1, which is 0 over 0. So we need to fix this problem. We need to factor the numerator with the pattern for the difference of cubes. So here's the pattern. A cubed minus b cubed equals a minus b times a squared plus ab plus b squared. This is a pattern you should have learned in Algebra 2, and you need to memorize this pattern. So in this case, all of our a values are x and all of our b values are 1. So when I substitute in, I have x minus 1, x squared plus 1x plus 1 squared, which is 1. And my denominator is still x minus 1. So now I can cancel out the factor of x minus 1, which would create a whole at 1. And we can substitute the 1 into the remaining polynomial here to find our value. So I have 1 squared plus 1 plus 1. So the limit as x approaches 1 is 3. Problem 4, again, we're getting 0 over 0. If I plug 4 in, I have 4 minus 4. And then I have square root of 4, which is 2. So I have 2 minus 2, which gives me 0 over 0. The strategy this time is not factoring. The strategy is multiply by a conjugate. We've used this strategy in other situations. The conjugate of a minus b is a plus b. If you look at the numerator and denominator, it's the special one that we're going to do the conjugate for. The special one is the one with the square root. So I'm going to do the conjugate of root x minus 2, which is root x plus 2. And I have to do the same thing for the numerator and the denominator. Oops. So the ones that are actually conjugates are in the denominator. I'm going to multiply those. And the other two, I'm going to leave them factored in hopes something cancels out. So in the denominator, I have square root of x times square root of x, which is the square root of x squared, which is just x. My middle terms are negative 2 root x and positive 2 root x, and those middle terms cancel out. This is the whole reason for multiplying by the conjugate. You want your middle terms to cancel out to give you something nice and simple. So the middle terms, negative 2 root x, positive 2 root x, those cancel out, so I'm not going to write them. And then I have negative 2 times positive 2, that's negative 4. In the numerator, I'm going to leave this factored as x minus 4 times root x plus 2. And now you can see that x minus 4 and x minus 4 can cancel out. So my simplified function is root x plus 2. Now I can substitute the 4 back in. So I have square root of 4 plus 2, which is 2 plus 2. And my final answer is 4. We're going to use the multiply by a conjugate strategy again in problem 5. This time our a minus b is square root of x plus 1 minus 1. So I'm going to multiply by its conjugate square root x plus 1 plus 1. Do that in the numerator and denominator. The pair that are actually conjugates you multiply. So I'm going to multiply the numerator this time. And then the other pair, we're going to leave them factored to see what cancels out. So in the numerator, square root times the square root gives you the square root squared, and they undo each other. So my numerator has x plus 1. The middle terms will cancel out again. That always happens when you multiply by the conjugate. So our last term is negative 1 times positive 1, which is negative 1. In the denominator, I'm leaving it factored, x times parentheses square root of x plus 1 plus 1. In my numerator, the plus 1 and minus 1 cancel, so I have x over x parentheses square root x plus 1 plus 1. And now my x and my x cancel. You need something in your numerator to hold that place, so I'm going to put a 1 there. And square root x plus 1 plus 1. So now when I do direct substitution, I should no longer get 0 over 0. I should be able to get an answer. So I'm going to substitute the 0 in for the x, and I have 1 over square root 0 plus 1 plus 1. Square root of 1 is 1, so I have 1 over 1 plus 1. My final answer is 1/2. And in problem 6, if I were to substitute the 0 in, I get the tangent of 0 over 0. Remember on your unit circle, tangent is y over x, and so this point right here is 1, 0. So y over x gives me 0 over 1, which is 0. Tangent of 0 is 0. So this is 0 over 0, which means direct substitution doesn't work. I need to do something to fix this. So this time I'm going to do a trig substitution. Remember that tangent is equal to sine over cosine. So I'm going to change my tan x to be sine x over cos x. And then notice we still have this x in the denominator. So now if you compare this to what we had to memorize from the top of our page, you'll see this sine x over x is actually a part of what we're evaluating. So we're going to split our limit into two pieces. We are going to write the limit as x approaches 0 of sine x over x times, so sine x over x is this piece right here. We still have a cos x in the denominator, so we need to do the limit as x approaches 0 of 1 over cos x. So the first limit we know now is defined as 1. The limit as x approaches 0, sine x over x, we memorized that on the top of our page, that answers 1. The second one we're going to do direct substitution, so put the 0 for the x, and I have 1 over cosine 0. Okay, remember that cosine is going to be your x value, so the cosine of 0 is 1. So 1 times 1 over 1, my answer is 1. All right, on page 2 of your notes, we have a piecewise function for number 7. For a piecewise function, you're trying to figure out, does the left limit equal the right limit? So x is approaching 3 from the left over here because it says x is less than 3. So this is the left side. And x is approaching 3 from the right over here. This is when x is greater than or equal to 3. So this is the right side. So I can write the limit as x approaches 3 from the left. And let's see, I'm going to plug the 3 into my left limit. 6 times 3 minus 4. I can also find the limit of f of x as x approaches 3 from the right, and I'm going to plug into the right-hand limit, and that's 3 squared. So here I have 14, and here I have 9, and the left limit does not equal the right limit, which means that the limit as x approaches 3 does not exist. In problem 8, we have the limit as x approaches 2 of f plus g of x. So the properties that we learned last class tells us that we can split this into two pieces. We can do the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. So here's our 2. As we approach 2 from the left and from the right, we're approaching the same number, and that seems to be a value of 1. So our first limit is 1. And our second limit, as x approaches 2 from the left and from the right, we're approaching the same number, and that number is 3. So this limit is 3. So we add them together, and we get the answer 4. Problem 9 is another piecewise function. You should try problem 9 the same way we did problem 7 before you continue watching this video. X is less than 4 in the second function, so that's the left side. X is greater than 4 in the first function, so that's the right side. So by plugging 4 into both of these, we can determine if the left limit and the right limit are equal. So the first one gives me square root of 4 minus 4, which is 0. And the second one gives me 8 minus 2 times 4, which is also 0. So because the left limit and the right limit are equal, the limit does exist, yes, and the answer is 0. Okay, the remaining 4 questions are questions that have been taken from Calculus AB, AP exam, so these are college level questions. In the first one, we're going to evaluate this limit. One thing that we're going to do is we're going to substitute for f of x the function f of x, which is 2x squared plus 1. And for f of 0, we're going to find the answer we would get if we put 0 for the x. So if I put 0 here, I square it, I still have 0, and times 2 is still 0. So 0 plus 1 is 1. So f of 0 is the answer you would get when you plug 0 into the function, and that's 1. So instead of minus f of 0, I'm going to write minus 1. And then over x squared, and x squared is going to say x squared for the moment. So plus 1 and minus 1, those cancel out. I get 2x squared over x squared, which is 2. So this actually simplifies to a constant function, y equals 2, always. So it doesn't matter what number x is approaching, y is always 2. In problem 11, we're going to substitute in 1. So we have 1 over ln1. So remember from our log unit, ln is log base e. So ln1 is saying e raised to what exponent gives me 1? And that exponent is 0. So this gives us 1 over 0. 1 over 0 is not the indeterminate form. It's not 0 over 0. This is simply a limit that does not exist. Okay, in problem 12, this is a piecewise function as x approaches 2. So we have a left limit over here. This is where x is less than 2, and this is our right limit. So by plugging 2 in, we should be able to see if the left limit equals the right limit. So if I plug 2 into ln x, I get ln 2. And if I plug 2 into x squared ln x, I get 2 squared ln 2, which is 4 ln 2. So my left limit is ln 2 and my right limit is 4 ln 2, and those are not the same value. So from the left and from the right, we're not approaching the same value, so the limit does not exist. And then problem 13 is a bit of a factoring question. You'll remember your difference of squares pattern is x squared minus a squared. It would be x minus a and x plus a. In order to factor the denominator, you have to remember that x to the fourth is the same as x squared squared. And a to the fourth is a squared squared. So you can still use your difference of squares pattern. So your denominator is going to become x squared minus a squared times x squared plus a squared. And then x squared minus a squared, that can factor just like we factored the numerator. So the denominator has x minus a, x plus a, x squared plus a squared, and then x minus a, x plus a. So these cancel and these cancel, leaving you just 1 over x squared plus a squared. Now we want the limit as x approaches a, so we're going to plug a in for your x values. So I have 1 over a squared plus a squared, and combining like terms, you get 1 over 2a squared. Alright, so you're going to turn the page to the classwork, and you should try all of the classwork problems before you continue watching the video. Okay, in problem 1, we try direct substitution. I have 5 times 1/2 plus 7, which gives me 2.5 plus 7, which is 9.5. So direct substitution worked just fine. And in problem 2, we're going to substitute 4 for the x. So I have 3 times 4 over 4 minus 3, 12 over 1, so direct substitution works just fine. In problem 3, If you substitute the 3 in, you're going to get 0 over 0, the indeterminate form. So we need to factor, and we're going to factor difference of cubes again. The numerator is x cubed minus 3 cubed. So following the same pattern that you have in your notes, this is going to be x minus 3, x squared plus 3x plus 3 squared, which is 9. So now we can cancel out the whole, and as x approaches 3, we're going to plug that value in. So I have 3 squared plus 3 times 3 plus 9, which is 27. Problem 4, plugging in 5 again gives us 25 minus 25 over 25 minus 25, 0 over 0. So we're going to factor. In the numerator, you have a common factor of x. So take that out, leaves you x minus 5. The denominator is difference of squares, which will be x minus 5 times x plus 5. So canceling out your whole, you have x over x plus 5. And now we can plug in our value of 5. So we have 5 over 5 plus 5, 5 over 10, which simplifies to 1/2. In problem 5, it looks kind of crazy, but we're doing the limit as x approaches -1. So remember, raising -1 to an odd power will keep it negative, and raising -1 to an even power will make it positive. So -1 to the 18 is positive, and this is just -1. In the denominator, -1 plus 3 times +1 minus 17 times -1 plus 19. All right, so in the numerator, let's see, we have a positive 8, a positive 2, that's 10. 10 minus 1 is 9. 9 minus 6 is 3, and 3 minus 7 is -4. In the denominator, we have 9 plus 17, that's 26, plus 3 is 29, and minus 1 is 28. And this will simplify by dividing it by 4, so we'll have -1 over 7. Number 6 is a constant function, y equals pi. So y equals pi always. It doesn't matter what number x is approaching, the y is always going to be pi. In number 7, the denominator is difference of squares, so the denominator will factor to be x squared minus 1 times x squared plus 1. And then that will factor further to be a denominator of x minus 1, x plus 1, x squared plus 1. In the numerator, we have x minus 1 to the 4th, so that's x minus 1 times x minus 1 times x minus 1 times x minus 1. So I'm going to just take one of those x minus 1s out. That leaves me 3 x minus 1s left. And the reason I took that out is so I could cancel it. So now I can plug the 1 in, and I should not get the indeterminate form any longer. I have 1 minus 1 is 0, 0 to the 3 is 0. The denominator is 1 plus 1, which is 2. 1 squared plus 1, which is also 2. So 0 over 2 gives me 0. 0 over 4 gives me 0. Problem 8, looks like we're going to have to multiply by the conjugate. So the conjugate of 2 minus root 4 plus x is 2 plus square root 4 plus x. You're going to multiply the numerator, so 2 times 2 is 4. The middle terms will cancel out, minus the square of the square root cancels out both the square and the square root, so we just have 4 plus x. The denominator, leave it factored, x times 2 plus square root 4 plus x. So distribute your minus here. This is 4 minus x So 4 minus 4 cancels. You have negative x now in your numerator. Negative x divided by x is negative 1. And now I have 2 plus square root 4 plus x. So now I can plug the 0 in, and I'll have square root of 4 plus 0, which is square root of 4, which is 2. So I get negative 1 over 2 plus 2, so I have negative 1/4. Problem 9 looks pretty tricky, but notice that the limit as x approaches 0, you're going to substitute 0 for all of these x's. So this becomes 0, this becomes 0, this becomes 0, leaving you just negative 7. 0, 0, 0, leaving you positive 7, and an answer of negative 1. And in the last problem, again, if we plug 2 in, we have 2 over 2 is 1, 1 minus 1 is 0. In the denominator, we also get 0, so we need to do something to fix this function. This time, our strategy is to simplify the fraction. So the first thing we're going to do is to combine the first two on the top, and I need a common denominator of x. So I'm going to multiply the 1 times x over x. Now my numerator is x minus 2 over x, and it's divided by the denominator. It's divided by x squared minus 4. I can change my divided by to multiply, and I can multiply by the reciprocal of x squared minus 4. So I have x minus 2 over x times 1 over x squared minus 4. I can factor x squared minus 4, so my numerator is x minus 2 times 1. My denominator has this x in it, and then the factors of x squared minus 4, so x minus 2, x plus 2. So now we see we have a factor that cancels out. My simplified equation is 1 over x times x plus 2. And now I can find the limit as x approaches 2 by plugging 2 in. So when I plug in 2, I have 1 over 2 times 2 plus 2, which is going to give me 1/8. Okay, that is the end of our notes for today.